Siemens panel bus burnouts can stem from several key factors. Overloading is a primary concern, and continuous loads exceeding 125% of the main breaker's capacity can lead to overheating and subsequent damage to the bus bar. Poor connections also play a significant role. Loose or damaged connections, whether at the breaker terminals or the busbar connections themselves, introduce resistance which generates heat and can cause arcing. A damaged breaker can also be a culprit. Faulty breakers may draw excessive current, again leading to overheating of the busbar. An undersized busbar for the intended load is another factor. If the busbar's current rating is not adequate for the demands placed upon it, overheating is likely to occur. When deciding between bolt-on and snap-on breakers, several factors should be taken into account. Bolt-on breakers are generally preferred for higher current applications, particularly when the continuous load may exceed 125% of the main breaker's capacity. Snap-on breakers are typically suitable for lower current applications, where the load remains within 125% of the main breaker's capacity. The individual fin ratings of Siemens busbars depend on the panel model and its amperage rating. A common rating is around 10 amps per fin for a 200 amp busbar. It's important to consult the manufacturer's specifications for the specific panel in question. While bus burnouts are occasionally seen in Siemens panels, it's not necessarily a widespread issue unique to this brand. However, it's a reminder that all manufacturers stress the importance of proper installation and adherence to load guidelines to prevent overheating and potential failures. To prevent Siemens panel bus burnouts, firstly, perform a thorough load analysis. This will ensure the panel is appropriately sized for the demands placed on it, and that all loads are within the rated capacity. Secondly, proper installation is critical. Always follow the manufacturer's instructions for secure connections and correct breaker spacing. Thirdly, regular inspection is essential. Periodically check the panel for any signs of overheating, loose connections, or visible damage. If you find continuous loads consistently exceeding 125% of the main breaker's capacity, it's prudent to consider an upgrade. This could involve switching to a panel with a higher amperage rating or installing bolt-on breakers. A deeper dive into these factors is warranted. Overloading occurs when the electrical demand placed on a circuit or panel exceeds its designed capacity. This excess current flow generates heat within the conductors and connections, leading to insulation breakdown, component failure, and potentially electrical fires. The 125% rule is a crucial guideline from the National Electrical Code, NEC. It stipulates that overcurrent protection devices, such as circuit breakers, should be sized no smaller than 125% of the continuous load. This margin of safety allows for sustained operation without nuisance tripping or overheating. Poor connections, whether due to loose terminals, corrosion, or improper insulation techniques, create points of high resistance within the electrical circuit. This resistance impedes the flow of current, converting electrical energy into heat. Over time, this heat can degrade the connection, further increasing resistance and escalating the problem. Arcing, a phenomenon associated with loose connections, occurs when current jumps across the gap between conductors. This creates intense heat and localized burning, which can quickly damage surrounding components and ignite flammable materials. Damaged breakers can manifest in several ways. A breaker might fail to trip under overload conditions, allowing excessive current to flow continuously through the circuit. Alternatively, a breaker might trip prematurely, disrupting power unnecessarily. In either case, a faulty breaker compromises the protection of the electrical system. The busbar, the central distribution point for electrical power within the panel, must be adequately sized to handle the total anticipated load. An undersized busbar becomes a bottleneck, restricting current flow and generating excessive heat. This can lead to warping, melting, and eventual failure of the busbar. Bolt-on breakers offer a more robust and secure connection compared to snap-on breakers. The bolted connection provides a tighter, more reliable contact, reducing the risk of arcing and overheating, especially in high-current applications. Snap-on breakers, while convenient for installation, rely on spring-loaded clips to maintain contact. These clips can loosen over time, leading to increased resistance and potential problems. The fin ratings of bus bars are determined by several factors, including the material, dimensions, and cooling characteristics of the fin. Each fin is designed to dissipate a specific amount of heat, allowing the bus bar to operate within its safe temperature limits. Exceeding the fin rating can lead to localized overheating and damage. Proper load analysis involves carefully assessing the electrical demand of all connected equipment and appliances. This includes determining the continuous load, which is the load that operates for 3 hours or more at a time, as well as the non-continuous load, which is the load that operates for less than 3 hours. The total load should never exceed the panel's rated capacity. Proper installation techniques are essential for ensuring reliable and safe electrical connections. This includes using the correct tools and torque specifications, cleaning conductors before making connections, and inspecting connections for tightness and integrity. Regular inspection of the electrical panel can help identify potential problems before they escalate into major issues. Look for signs of overheating, such as discoloration, melting, or burning smells. Check for loose connections, damaged components, and any other abnormalities. Infrared thermography can be a valuable tool for detecting hotspots within the panel. This non-contact method allows you to visualize temperature variations and identify areas of concern. Upgrading the electrical panel may be necessary if the existing panel is undersized or outdated. A larger panel provides more capacity for future growth and can accommodate heavier loads. When upgrading, it's important to choose a panel that meets the current and future electrical needs of the building. In addition to the above, consider the ambient temperature in which the panel is installed. High ambient temperatures can reduce the panel's capacity and increase the risk of overheating. Ensure adequate ventilation around the panel to allow for proper heat dissipation. Regularly clean the panel to remove dust, dirt, and debris, which can insulate components and impede cooling. Use a vacuum cleaner or soft brush to gently remove any accumulated material. Avoid using compressed air, as this can simply redistribute the dust and debris. If you are not comfortable working with electrical equipment, it's always best to consult with a qualified electrician. Electrical work can be dangerous, and improper installation or repairs can lead to serious injury or property damage. Consider energy-efficient appliances and lighting. Reducing energy consumption can lower the overall load on the electrical system and reduce the risk of overloading. Check for any signs of rodent or insect infestation. These pests can damage wiring and components, creating potential hazards. Seal any openings in the panel to prevent them from entering. Keep flammable materials away from the electrical panel. Storing combustible items near the panel can increase the risk of fire in the event of an electrical fault. Ensure that all circuit breakers are properly labeled. This makes it easier to identify the correct breaker for each circuit and can save time and prevent confusion during troubleshooting or maintenance. Consider installing surge protection devices. Surge protectors can protect sensitive electronic equipment from voltage spikes, which can damage or destroy components. Voltage spikes can be caused by lightning strikes, power outages, or other electrical disturbances. Make sure all electrical work is performed in accordance with local codes and regulations. Electrical codes are designed to ensure the safety and reliability of electrical systems. Familiarize yourself with the relevant codes and follow them carefully. Use only approved electrical components. Approved components have been tested and certified to meet safety standards. Avoid using counterfeit or substandard components, as these can be unreliable and potentially dangerous. Regularly test ground fault circuit interrupters, GFCI. GFCI are designed to protect against electrical shock by quickly cutting off power to a circuit when a ground fault is detected. Test GFCI monthly to ensure they are functioning properly. Install arc fault circuit interrupters of SI. SI provide enhanced protection against electrical fires by detecting arc faults, which are dangerous electrical conditions that can ignite flammable materials. SI are required in many areas for new construction and renovations. Conduct a professional electrical inspection. A qualified electrician can perform a thorough inspection of your electrical system to identify potential hazards and ensure that it meets safety standards. This can help prevent problems before they occur. Document electrical modifications. Keep a record of any electrical modifications or repairs that have been performed. This information can be helpful for future troubleshooting or maintenance.